Our pleasure to welcome Łukasz Cholewa from the Krakow University of Economics. We'll give a talk about Lorenz map, renormalizations, periodic orbits, and the connection to the Lorenz system.
Thank you very much. And thank you for the opportunity to give a talk here. The talk will be based on joint work with Piotr Oprocha, renormalization in Lorenz maps, complete invariant sets and periodic orbits, and with Eran Igra, needing the Lorenz. Presentation plan is as follows. At first, I will define the main object of our study, that is expanding Lorenz maps, and I will introduce basic concepts from needing theory. Then I will discuss our main results with Piotr about relationships between renormalization and completely invariant sets. The motivation for our work comes from the theory of Ding. Ding claimed that there is a one-to-one correspondence between renormalizations and proper completely invariant closed sets. However, we were able to find examples showing that it's not true in general. So, motivated by this observation, we will provide an algorithm to distinguish the renormalizations that can and cannot be recovered from completely invariant sets. This way, we correct some gaps existing in the operator. And the second part of my talk will be based on work with Eran Igra. I will discuss the connection between expanding Lorenz maps and the Lorenz system. Okay, so expanding Lorenz maps are interval maps satisfying the following three conditions. So there is a critical point, and that is a point of discontinuity, C, such that F is continuous and strictly increasing on both subintervals AC and CB. There are one-sided limits at the critical point C equal to B and A, and F is differentiable with slope greater than 1 everywhere except at most a finite set. Note that the last condition implies that the set of all three images of critical point is dense in interval AB. Okay, a few words about motivation, why people study these maps. So, at first, Lorenz maps appear as a Poincar maps or reduction of Poincar maps in geometric models of Lorenz attractor. I will tell more about it in the second part of my talk. But independently, Lorenz maps occur in economics, in some models of financial markets, and they also occur in neural dynamics. Okay, so needing theory allows us to encode trajectories of points under the Lorenz map by binary sequences. So for any point X that is not a pre-image of critical point C, we define the needing sequence as a binary sequence such that if the end iteration of point X under the map F is on the right from the critical point, then the end symbol is 1, and if it's on the left from the critical point, then the end symbol is 0. For points that are free images of the critical point, we define upper and lower leading sequence as such limits, where the limits are calculated to points y which are not free images of a critical point C. Okay?
And this is well defined.
Yes, this is well defined. And this is a classical result, classical theory. Okay, and the pair KF of the two binary sequences that encodes, let's say, one-sided trajectories of a critical point. This pair is called the leading invariant of F. Okay, so a quick example. Here we have a expanding Lorenz map with constant slope, so-called beta transformation. And here the right side limit at critical point C is 0, then 0 goes to f of 0 goes to f of 1, and then f of 1 goes to f of 0, and this is a two-periodic orbit. So in this case, the leading invariant of the map F will be 0, 1, 0, 0, 1, 0, 1, 0, 1, and the second sequence is 0, 1, 1, 0, 1, 0, 1, 0, and so on. Yes.
I have a question. I'm sorry because I missed this in the beginning. So, is the map defined at C, or is this a gap?
For simplicity, we define map C to take value 0 at critical point. Yeah.
Because I was asking because it would make sense for this one. But
yeah.
Okay.
But if C is not periodic, wouldn't the plus and the minus present?
They cannot coincide. Eta plus and eta minus, they can.
If we get expanding
Different, they can means because it doesn't be part of one.
Okay. A few words about lexicographic order and the shift map. So we introduce a standard notion of lexicographic order. So the sequence X is greater than, less than sequence Y. There is a position K such that both sequences agree for indexes from 0 to K minus 1, and at the position K, xk is less than yk. Okay, and we denote by sigma the standard shift map. Okay, so the important thing about leading invariants is that the leading invariant characterize expanding Lorenz maps. This is classical result by Hubbard and Sparrow. And it says that if I have expanding Lorenz map F with leading invariant eta plus and eta minus, then these two sequences have to satisfy this condition for all n. And in the other hand, if I have two binary sequences that satisfy this condition for every n, then there is an expanding Lorenz map with such a leading invariant. Okay, and another thing, if two expanding Lorenz maps have the same leading invariant, then they are conjugate by a homomorphism of the interval AB. Okay, so let F be an expanding Lorenz map with leading invariant KF. Recall that CF is a set of all pre-images of critical point C. And the set of the leading sequences of all points for a map F is completely described by its leading invariant KF. So this is the set of all symbolic itineraries of all points of all points of the map F. So it is completely described by two sequences eta plus and eta minus that form a leading invariant of map F. Okay. Before I define the renormalization of the Lorenz map, let's see an example. So here we have again theta transformation F. And here we have a graph of the second iteration of this map F, so F squared. And we can observe that in this smaller square here, we have again an expanding Lorenz map. In this case, it will be a doubling map. So if I take a map G that is F squared restricted to this smaller interval U B, then this map G is again an expanding Lorenz. From the symbolic point of view, if I consider the leading invariant of this map F, we already know it has this form. I can write these sequences in such form using two words omega plus and omega minus. So I can write the leading invariant of this map in this way. So keep this example in mind and now go on. Okay. So yeah, as I said before, when we rescale the map G to 0, 1, then we get a doubling map. And by replacing omega plus with 1 and omega minus with 0, we get a leading invariant of this new map G, of the doubling map.
Wait, so this works because the critical point is periodic. Is right? So if it weren't periodic, the omega plus, there's no chance for omega plus or omega minus, or it's still a chance?
It's still a chance.
Okay.
Yeah. You will see a definition of renormalization from the symbolic point of view in the few next slides.
Okay, sorry.
Okay. So let F be an expanding Lorenz map, and if there is a proper subinterval UV that contains a critical point C, and there are integers L and R such that the map G defined in this way, so this is S to the L on the left from the critical point, F to the R on the right from the critical point. If this map G is itself a Lorenz map on this smaller interval UV, then we say that F is renormalizable, or that G is a renormalization of F. And we write shortly G is equal to F to the L, F to the R. And the interval UV is called renormalization interval. Okay. So yeah, the map G from the previous example is a renormalization of the map F. Okay, and another definition, if we allow that one of the numbers L and R is equal to 1 and the second one is equal to 2, and we still have a map G that is defined in this way, and it is itself a Lorenz map on interval UV, then we say that F is trivial renormalization, or that G is a trivial renormalization of F, and we use the same notation. And in this case, we do not require that the set UV is smaller than AB. It might be equal to AB. Okay, and now
explain the etymology of this notation. Why do you call it renormalization?
I don't know. I mean, that procedure looks like that. Look this way, that you are taking some iteration of the original map, and if you see around the critical point that you have again a Lorenz map in smaller interval, then you rescale it. So it's, I don't know, renormalize it to again to the map from the same class. I don't know. Maybe this is the reason why we call it renormalization.
Might come from physics, because normalization in physics was a similar idea that say you have some large collection of electrons with interactions in them, and then you scale, and you see that in the scale picture we have somewhat similar interactions between now already blocks of electrons. So I think the term came from physics.
But this is a subsystem, right? Because after we renormalize, we forget about the others because everything is inside of this smaller. Even though that you allow L and R to be non-equal. But let's say in your example, L was equal, R equal 2, and then you got a subsystem. I mean,
It's kind of first return.
Yeah, it's first map.
Yeah, this is subsystem.
Or not necessarily first, but return map.
Similar to
But what they found out to be interested in a limit object of this process. I mean, it's always the goal is to be interested in a limit object of this process in something.
Not always. I mean, for example, for a beta transformation, and here maybe not only for beta transformation, but if you assume this extending condition with derivative, then you can have only finitely many renormalization maps, because after each renormalization, the slope grows.
In some cases, I assume, because this is the case of complex dynamics, there's a huge difference between the behavior of map which is infinitely renormalizable and not infinitely.
Yes.
So that gives you a very distinct situation.
In our case, you can only get finitely renormalization because the assumption on the okay, and there is also a symbolic approach to define a renormalization. So let Kf equal to eta plus eta minus be a needing invariant of the map R, and let omega minus omega plus be words of lengths L and R, both greater than 1. Then we say that the leading invariant KF is renormalizable by words omega plus and omega minus if the sequences eta plus, eta minus can be expressed in the following way. So in our example, we had this case, but it also may be something like that. So in this case, it is not pre-period. And we have analog of the trivial renormalization in analytic approach. So if this condition is satisfied for words of length 1 and 2, so the leading invariant is renormalizable by words 1, 0, 1 or 1, 0, 0. Then we say that it is trivially renormalizable. Okay, so as I said in our example, G equal to X squared, F squared is a renormalization of F, and the leading invariant is renormalizable by words 1, 0, 0, 1. Okay, so now let me recall the results of yielding thing from word renormalization and alpha limit set for extending Lorenz maps. At first, a definition: a non-empty set E is said to be completely invariant under F if it's equal to its image and to its pre-image. Okay. So the one of main results of Ding's paper says that for given extending Lorenz map F, there is a one-to-one correspondence between the renormalizations and proper completely invariant closed set of F.
Maybe but it was not for before this, there was a schema of metaphysical form.
It's pure development. And later people realized some phenomena hold also for long. Mathematics of terminology and from modern or multimodal big paper that linear test from.
Here by renormalization, you need the choice of subinterval and the iterates LR.
Yes. I mean, this analytical definition. Okay, so more precisely, for any open set U, we denote by end of U the first iteration when this set covers the critical point. Sorry, it should be capital F here. Okay, so precisely the Ding's theorem says that if I have proper completely invariant closed set, then I can construct a renormalization using the following procedure. At first, I look at 2 points, E minus and E plus, that are the closest points from the set E to the critical point C on the left and on the right of the critical points. Then I compute L and R. So L is the first iteration when this interval E minus C covers the critical point C, and similarly for the number R. Then the point E minus is L periodic, E plus is R periodic, and the map defined in this way is a renormalization of map F. Okay, so we have procedure how to product renormalizations from completely invariant sets. On the other hand, if G is a renormalization of F, then there exists a unique proper completely invariant closed set E that defines renormalization G by the procedure from the first part of theorem. Okay, so the idea of the second part of this theorem is as follows. So let G be a renormalization of F, denoted by JG the set of all points whose trajectories never intersect the open renormalization interval UV. Then we prove that JG is a proper completely invariant closed set, and we put E is equal to JG. So this is the idea of proof. But it turns out that the set JG may be empty. It may happen that there exists several different renormalizations that define the same set JG. And it may happen that the set JG is not completely invariant. We have examples of every of these scenarios. And note that if there exists a proper completely invariant set E such that it defines the renormalization G, then this set must be equal to JG. So our examples not only show gaps in the proof, but also they show that the second part of Ding's theorem is not true in general.
The first one is what?
The first one is correct with small changes, but small thing. You just need to exclude singleton as set E, because a singleton, if our map has a fixed point at 0 or 1, then 0 or 1 may be a closed completely invariant proper set, but it cannot define any renormalization. So you just need to exclude this case, and then everything is fine. Okay, so the question is, which renormalization can and cannot be obtained from the procedure described in the above theorem? So our goal was to answer this question. And in order to answer this question, we introduced the notion of basic renormalizations. So the basic renormalizations are just renormalizations, trigger renormalizations, and renormalization f squared. And the idea is to present a given renormalization as a decomposition of basic renormalizations, and then look at the components in this decomposition. Okay, so I will describe it in detail in the moment. Note that basic renormalizations correspond to renormalizations of needing invariant by words 1, 0, 1, 1, 0, 0, and 1, 0, 0, 1. Okay, so our algorithm is based on the following procedure or a decomposition. So assume that an expanding Lorenz map F has a basic renormalization, maybe trivial, or this one F squared. Assume that it has a basic renormalization F1. If F1 also has a basic renormalization, we denote it by F2. Otherwise, we put n equal 1 and the process of renormalization is complete. So basically, at each step, we want to renormalize a map using one of the basic renormalizations. Proceeding this way n times, we obtain a sequence of Lorenz maps. At each step, we obtain expanding Lorenz maps as a renormalization of the previous expanding Lorenz map. So this is the sequence of expanding Lorenz maps, such that the next one is a basic renormalization of the previous one. And F0 is the first map. Okay. One can observe that for A equal to 1 to the n, there exist numbers Li, Ri, such that we can write the map Fi in this form. So Fi is equal to F to the Li on the left from the critical point and F to the Ri on the right. Okay, and the main observation is that if Fi is a trivial renormalization of the previous map, then trajectories of all points from open renormalization interval U I minus 1 to V I minus 1 intersect the open renormalization interval of the next map, and consequently in this case it should be a capital F and capital F. The sets JF I minus 1 is equal to JF I. So if during this renormalization process I have a trivial renormalization, then it won't correspond to any new set JG. This is the idea. And we proved with Piotr that the following trichotomy holds. The map Fn equal to F to the Ln, F to the Rn is the composition of, okay, so this is the first case. So at some step of this renormalization process, I get map Fn, and this is equal to F to the Ln, F to the Rn. And the first case is when Fn is the composition of n trivial renormalization. So at each step, before I get map Fn, at each step I use the trivial renormalization to obtain another map. In this case, the set JFN can at most contain one of the endpoints of the interval. So even if it's not empty, I cannot use it in Dink's procedure to obtain renormalizations Fn. And also note that in this case, the numbers Ln and Rn are different. The second case is that okay, I have map Fn, and this map is the basic non-trivial renormalization of the previous one. In this case, the set JFN corresponding to this renormalization contains a periodic orbit. And if I use this set JFN in Dim's procedure, then I will obtain renormalization Fn. So in this case, everything works. And note that in this case, numbers Ln, Rn are equal.
So you may put this in mind to assume that after n you cannot longer renormalize, which is
No, Fn is just any renormalization that you get at this renormalization at any state of okay, and the last case is that there is non-trivial renormalization in the process, but not the last one. So Fn is a trivial renormalization of the previous map, but somewhere earlier we saw a non-trivial renormalization. For some I less than n. And in this case, the set JFN is non-empty. It contains a periodic orbit, but if we use it in Dim's procedure, then we won't get renormalization Fn. We will get the sum of the previous renormalization, some of the previous renormalization. In fact, we will get renormalization Fj, where J is the largest index for which the map Fj is non-trivial renormalization of the previous. And also, in this case, the numbers Ln and Rn are different. So in fact, only in the second case we can obtain renormalization Fn as a result of Dim's procedure.
So in other words, Dim's theorem works only if Ln is equal Rn. This is what this means?
We don't know. I mean, here we have this trichotomy only for renormalizations that can be obtained in this renormalization process. Okay. And we don't know if all the renormalization can be obtained in this way. So yeah, as you observe, the set JFN is non-empty and defines the renormalization Fn if and only if the numbers Ln and Rn are equal, but we assume that Fn is obtained in this renormalization process. We don't know what happens in general situation. We know that not all renormalizations can be obtained in this way. Probably if the map F has a constant slope, then probably all renormalization can be obtained this way, but for a non-constant slope, we have examples of renormalizations that cannot be decomposed into basic renormalizations. So for non-constant slope, it may happen possibly that there are renormalizations with different numbers L and R that can be obtained from this procedure, but we don't know. Okay, maybe just a quick example of this process. So here we have again a Lorenz map with constant slope, and I will show you how this renormalization process looks like. So here on this green interval, we will have a renormalization that is trivial one. So it's T1 equal to T squared. And then this map T1 also will have renormalization at this smaller green interval. And again, it is a trivial renormalization. So T2 is a trivial renormalization of T1. and it is the renormalization t cubed t squared of our initial map t. And this map again is renormalizable. It is renormalizable on this small interval P4 Q4. So after this renormalization, we get this small in this small the map in this small square. But this time it's a non-trivial renormalization. So T3 is non-trivial basic renormalization of the previous one, and it is the renormalization of the initial map T, T to the 5, T to the 5. Okay, and in this example, the renormalization T2 with different numbers L and R cannot be recovered from the corresponding set J2. And the set J3 corresponding to this renormalization, the free contains periodic orbit, and if you use it in Ding's procedure, then everything is fine. You will obtain the map. Okay, and also one example from the perspective of the needing theory.
So can you say that that is like an outcome that you were able to locate periodic orbit?
Sorry?
I mean, okay, so let's say you have done this. I'm trying to understand what does it say that we have found this small.
Okay, so perhaps I should say before. Renormalization are related to many other properties like topological transitivity. They are related to the existence of some special periodic orbits, so-called NK cycles, primary NK cycles. And yeah, I will try to show you one result in the second part of my talk, when we use renormalization to describe the set of periodic the set of periods of a given map. So if you have a map that is renormalizable, then its renormalization gives you some information about periods.
Right. And can you also comment, how do you know that the procedure ended in the example?
In this example?
In the previous one.
In the previous, okay. In the previous one.
This one, yes.
Let me think. I'm not sure if, I mean, perhaps they can be another renormalization.
Ah, okay.
So I'm not sure if the procedure ends here, but as I said before, in our theorem we can stop at any time during this renormalization process and say something about the current renormalization. So there possibly they can be another renormalizations, but
It seems you really care about periodic orbit. This is why you stop.
Sorry.
I don't understand. Why did you decide to stop it? That's
Because we have two examples, one where it's working,
Yeah.
one where it's not.
Yeah. We are
I see.
yeah.
Okay.
So this is an example and a counterexample at the same time, so that's
Yeah.
why it's nice.
Yeah. Okay, and here we have another example, this time from the perspective of the needing theory. So here we have a map H with the following needing invariant. We can find the parameters beta and alpha that define map with such a needing invariant. So here. Okay, so here we can write the leading sequences in this way using words 0, 1, 1, 0. So this is renormalization of the leading invariant that it's not trivial. So the first renormalization is not trivial, and then we just instead of omega plus write 1, and instead of omega minus 2 we just write 0. And this way we obtain the leading invariant of renormalized map. And this renormalized map again can be renormalized. This time it has trivial renormalization by words 0, 1, 0. And again, I repeat this procedure and obtain another map H2, which again is trivially renormalizable, and so on and so on. Okay, so in this process, only the first renormalization was non-trivial. So only the first one was non-trivial, the rest was trivial renormalization from the previous one. So in this case, all these sets JH1 to JH4 are equal. And this set defines only the first renormalization J1. Okay, so as I said before, we don't know, so we left it as an open question. Is it possible to obtain a renormalization G with different numbers L and R using the procedure from the Ding's theorem? We don't know, but we expect that it cannot be a map with constant slope. There are some results that suggest that in constant slope case any renormalization can be decomposed into basic renormalizations. So we already know that for different numbers L and R, the renormalization cannot be in this case obtained from Ding's procedure. But in the case of maps with non-constant slope, we don't know.
So it's different between constant and slope, because for maps of we want to think about not always, but understand assumptions you can conjugate with constant slope. You have here that kind of theorem.
Yes.
Under what conditions?
Yes. They can be semi-conjugate, and I think
wandering interval not be minimal language.
I think
That's why the same.
yeah. I think you can always semi-conjugate them, but the full conjugacy is only in some cases. But I think in many cases, for example, if you have slope everywhere greater than square root of 2, then you have transitive map, and I think every transitive Lorenz map is conjugate to beta transformation to Lorenz map with constant.
I heard what you told and how that something holds for constant slope, something doesn't.
Yes.
There must be some troubles with the conjugate.
Yes, and we just have example of map with non-constant slope that has a renormalization f cubed, and this is the minimal renormalization. So you cannot decompose it into trivial or basic f squared renormalizations. So this is why. So in that case, our result doesn't fall.
Will you show that example?
I don't have it at
Okay.
this presentation.
It's crazy difficult.
No, it looks like if I remember, it changes the slope here, then it goes here and changes it again.
So it's still piecewise linear.
Yes, yes. And yeah, piecewise linear, and it changes the slope in 4 points.
But the slope is still bigger than 1.
Or more. Yes, yes. Everywhere is greater than 1. So yeah, it's more like that. Thanks. It's very easy. In fact, we just took the simplest needing invariant that cannot correspond to map with constant slope. There are some results that indicate when it can and when cannot correspond to constant slope. And then we just find some parameters and find an example of such map. Okay, so now I will move on to the second part of my talk, which is based on the joint work with Eran Igra. Unfortunately, unlike Eran, I'm not specialist in three-dimensional flows, so I won't go too much into details, but I just want to say something to give you a context of our work. So recall that the Lorenz system here defined by positive parameters sigma, rho, mi is defined as the flow generated by the following three-dimensional system of differential equations. And Lorenz observed that at the parameter values, so here we have the classical parameter values that were studied by Lorenz, the flow generates a chaotic butterfly-shaped attractor like you see here. Okay, so in order to understand the dynamics on the Lorenz attractor, the simpler objects were introduced. The simpler objects, I mean geometric models of Lorenz attractor that looks more or less like this one on the picture. And here if you the first little map is marked on green, and you can reduce the first return map to interval map that is Lorenz map or Lorenz like.
Sometimes yes, sometimes no.
Yes. Yes.
No. So the matter is whether there is invariant correlation to this blue line.
Yes. My point is that the relation between geometric models and Lorenz or one-dimensional maps are more or less understood. The problem is what's the relation between Lorenz system and geometric model. So it is a small fourth problem. Fourth problem. Is the dynamics of Lorenz system at the classical parameters equivalent to that of the geometric model? This question was answered by Tucker. So Tucker used rigorous numerical methods to give an affirmative answer to Smith's question. But the question about more general set of parameters is open. However, recently, Talipinski in her paper established analytically a relation between the Lorenz system and the so-called extended geometric model for a certain set of parameters that we denote T. And at such parameters, the Lorenz system can be continuously deformed to the extended geometric model. Okay, so we know what the relation between, more or less, we know what's the relation between geometric models and one-dimensional maps. The problem is relation between Lorenz system and geometric models. So this is the problem. This is the reason how to, in fact, it's hard to say something about Lorenz system using one-dimensional model, one-dimensional map. So in our work with Eran, we tried to establish relation between Lorenz system for some parameters and Lorenz maps. It was our goal. And we used the results from this paper of Talipinski, so I will recall some key aspects of this work. So in this work, it was defined the set of parameters P, and for every parameter from this set, the Lorenz system has a cross section configured as follows. So we have fixed points P0 of P1. Here are the at the border of cross section R, and we have invariant manifold, stable invariant manifold of origin that intersects this cross section R in arc W, and this arc W partitions R into two topological rectangles, R0 and R1. And she also proved that in this case, the first return map B is well defined and semi-conjugate on its invariant set in the sum R0, R1 to some subsheet. Okay, so this is the picture how more or less it looks like for such parameters in this set P. Moreover, there exists a collection of parameters T, so-called trifold parameters, such that for each parameter from this set, there is a pair of heteroclinic trajectories connecting 0, 0 and P0 and P1. And if you also connect it with point of infinity, then you will get trefoil knot. So that's the reason why we call it trifold parameters. The first return map is semi-conjugate on its invariant set to the full shift onto symbols. So in particular, it has infinitely many periodic orbits. So this is how this situation looks like. Okay, and we build our results using these sets of parameters T and P. So yeah, maybe at first I will say something about needing invariant of the Lorenz system. So before I move on to our results, consider the Lorenz system given by parameter B. So we have a situation that looks like that. And here we define the needing invariant of its attractor to be the pair of sequences that describe the itineraries of separators gamma 0 and gamma 1. So they just encode the position of the consecutive intersections with these separators with the cross section R. So if the intersection point is in R1, then we have symbol 1, and if intersection point is in R0, then the corresponding symbol of this sequence will be 0.
Can you clarify, because before that we were dealing with one dimension. Here it seems a priori we have something two-dimensional, but now we are talking about the moving sequence. So
here we define needing sequences for attractor, and then I will discuss the relation of these needing sequences with needing sequences of Lorenz map.
I see. Okay. I left the handle right? No, I understand that, but I was looking for more rigorous problems. So there is no one-dimensional model? There is, but for what parameters it works? Okay, let's wait with patience.
Yeah, and here note that these sequences are periodic precisely when gamma 0 and gamma 1 are homoclinic trajectories to the origin. Okay, and just one technical comment. So there is an open set O, a subset of P, which is the neighborhood of the set of parameters C, such that for each parameter from this set O, the first symbol of omega 0 is 1, and the first symbol of omega 1 is 0. So that is the separators omega 0 and gamma 0 and gamma 1 satisfy the following. So after gamma 0 leaves the origin, it tends to, I will show, after gamma 0 leaves the origin, it tends to P1 in the case when parameter B is also in the set T, or its first intersection point with the cross section R is transverse and lies at R1. Similar like at this picture. And we have similar property for gamma 1. So after it leaves the origin, it tends to P0 in case when parameter V is in the set T, when we have this heteroclinic connection, or its first intersection with the cross section transverse and lies at R0. So we know that there exists a set of parameters, and this is important because our our reduction to one-dimensional map will be made for Lorenz system defined by parameter from for Lorenz system defined by any parameter from the set O.
Excuse me, somehow the picture looks counterintuitive. The expect that gamma R1 on the picture intersects R1.
Gamma 1, it intersects R0.
I mean, if you judge by the picture, I think that it's a true intersect R1.
Yeah, that's the problem with three-dimensional vectors, they show nothing.
What say it should
Yeah, it looks like it intersects on the right.
okay, but this cross section ends here. I mean,
Oh,
P1 is yeah.
Compact.
The right hand side. Excuse me, what are the yellow patches?
First return map of the flow. Of course, it may be much more complicated. This yellow region may be much more complicated. It's the plot of the first return map.
So on the one side is yellow part, because the time we spend to come there is very close to this vertical V something, the green, very short to the saddle, and very close to the saddle. So it spends a lot of time, and there's the time for contraction. When for contraction, you are saying very. I don't understand why on the other side of it. In practical, one side time, but it was a long time. Think about splitting the big rectangle into two sides, and we think about go to the center. Because it is always stable in the center. So if you are close to it, then it's easy. It's a very long time.
Okay. So just one definition or maybe notation. So we will consider family of symmetric beta transformation given by this formula where beta is from 1 to 2. So this map looks like that. And okay, and for every beta, this map has a critical point at 1/2, and by I beta we denote the maximal invariant set for F beta in 0, 1 minus 1/2. So explicitly I beta is equal to the whole interval minus the set of all pre-images of critical point 1/2. Okay, so our result says that if I have parameter V from this set O, then there is a parameter beta, so slope that depends slope of the of interval map of symmetric beta transformation that depends on this parameter V, and there is an invariant set for the first return map such that the following condition holds. So there exists a continuous surjective map phi, so such that this equality also the first, in other words, the first written map on its invariant set is semi-conjugate to the symmetric beta transformation. Moreover, if X is a periodic point of beta transformation, then the pre-image of our semi-conjugacy of the point X includes at least one periodic orbit for the first written map of minimal period n. Okay, so we can say something about periodic orbits of first written map in the Lorenz system using our symmetric beta transformation. And the next thing is that if the leading invariant of f beta consists of non-periodic sequences eta plus and eta minus, then it agrees with the leading invariant for the Lorenz system at given parameter v. I will explain what does it mean that it agrees. So here we have our first written map, and here we have our reduction to one-dimensional map. Observe that firstly we get an interval map with fixed points 0 and 1, but then we just take this map in this smaller square. This is the Lorenz map, and we rescale this map in smaller square again to interval 0, 1, and this way we obtain symmetric beta transformation. So yeah, that's why we don't have this point that corresponds to these fixed points P0 and P1. We don't have them because of this modification. However, one can observe that any point except this fixed point 0 and 1 eventually intersect this smaller interval here, and they stay there forever. So we only lost information about this. We only lost these fixed points. Okay, and what about the leading sequences? So our result says that if I have this parameter v, I have a beta that depends on v, and k of v is a leading invariant of the attractor, so it encodes the intersection points of gamma 0 and gamma 1, and kf beta is a leading invariant of symmetric Lorenz symmetric beta transformation, so it encodes the trajectories of one-sided trajectories of critical points. Okay, so we have that then the precisely one of the following conditions hold. So the first case is that the leading invariance of attractor and of the Lorenz map agrees. So observe that here we have to take a shift of the sequences eta minus and eta plus, because these sequences omega 0 and omega 1, in fact they encodes the trajectory of they correspond to trajectory of 0 and 1 on the interval. So since the needing invariant of Lorenz map is a pair of sequences that encodes the trajectory of critical point, we need to take a shift to have needing sequences that describe the trajectory of 0 and 1. And the second remark is that here omega 0 will correspond to eta minus of 1, so the trajectory of 1 on the interval, and omega 1 corresponds to eta plus of 0, so the trajectory of the point 0 at the interval.
When there is a frequency, so P0 and P1 are fixed points.
P0 and P1 are fixed points.
Yeah. They are. That's why this yellow is very sharp.
Right.
But for the blue go around.
Yeah.
So they go under the semiconductor to 0 and 1.
Sorry?
The points P0 to P1 go under semiconductor to 0 and 1.
Yes, but then we get this Lorenz-like map with fixed point 0 and 1, but we prefer to work with this Lorenz map more for that.
Could you please repeat, so you define here the semi-conjugacy and this I mean, I don't understand the reduction formally.
Okay,
That's
so
what I said more or less. There is foliation on this rectangle. Foliation parallel to the line, more or less parallel to the line which splits to the left rectangle.
Okay.
If there is foliation, you have factorization along the edge of the foliation. Foliation won't be invariant. There is a chance because there is contraction in the direction. There is a chance to have. So if you don't have foliation, there may be a lot of part of the shape is foliated. Maybe no dense, but big. And that's if this is so, you have hyperbolicity, not uniform path. Hyperbolicity is the Platonic point.
Okay, but I'm asking about the content of the slide. Are you describing the result of a theorem? I mean, there is such a code.
now I'm describing the last part of this theorem, because I said here that if the needing invariant of the symmetric beta transformation f beta consists of non-periodic sequences eta plus and eta minus, then it agrees with the needing invariant for the Lorenz system at this parameter.
Okay,
And
how do you prove that statement?
Okay, I don't have it.
So you are just describing the correspondence, but not the mechanism that gives it. Okay.
Yes.
But the existence of the semiconductor is a part of the theorem, right?
Yes, the existence of the semiconductor is guaranteed by the first part. Yes, and I just explain what exactly it means that this needing invariance agrees. Okay.
For good parameters.
So yeah, the second case is if the needing invariant of the attractor is not equal to this pair of sequences, so shifted needing invariant of beta transformation, then it means that the sequences eta minus and eta plus are periodic. So there exists some k, a number k, such that eta minus and eta plus are both k periodic, and they agree with needing sequences of Lorenz system for position from 1 to k minus 1. So it agrees for some position, and then it becomes periodic. So they are like periodic cut off of the meeting invariant of Lorenz attractor. So this is because during the deformation of the first return map to one-dimensional map, at some point the form of meeting invariant of attractor may be destroyed, and then it becomes periodic. I mean, the resulting one-dimensional map has a periodic needing invariance. Okay, and we remark that when the parameter v tends to some trefoil parameter, then the corresponding parameter beta, the slope of corresponding symmetric beta transformation, tends to 2. And in particular, for parameters from the set T, the corresponding beta transformation must be a doubling map. Okay. I don't have a lot of time, so I will just say a few words about methods that we use to study the symmetric beta transformations, and then we use the obtained information to say something about a Lorenz system. So let me quickly recall the definition of primary NK cycles. So primary NK cycles are some special periodic orbits of expanding Lorenz maps that behave in the nice way, and they are related to existence of renormalizations. So I will just show you example. So here we have example of a primary 5-2 cycle. It means that I have 5 points ordered with increasing. The indexes are ordered increasing. Yeah. And so I have 5 points, and this number 2 means that I after each iteration the index jump by 2, and when it exceeds 5, then I will take modulo 5. So yeah, so Z0 goes to Z2, Z2 goes to Z4, Z4 goes to Z1, and so yeah. And another thing is that the image of 0 and 1 must be between ZK minus 1 and ZK. So in this case, between Z1 and Z2. So this is periodic orbit that behave in a sense in a nice way. I will show you how the dynamics of a map with a primary 2-1 cycle looks like. So consider interval Z0, Z1. After first iteration, this green part goes to the left, and it goes to C1, Z1 goes to A, Z0. This orange interval Z0, C goes to Z1, 1, or B, it should be B, sorry. And after second iterations, they again meet in the interval Z0, Z1. So they travel in such cycle. Okay. And in more general case, when we have prime and cycle, then again this interval around critical point is split into two intervals. This green one goes to the left, and the orange one then goes to the right. Then they glue together again, and then they travel together, and after n iterations, then again cover this interval Zn minus k minus 1, Zn minus k. So there is a relation that if you have a primary NK cycle, then the map has a renormalization f to the n, f to the n. So, so then we have such a property, and this is also nice because we have explicit formulas describing the regions in parameter space of beta transformations where given beta transformation has a primary NK cycle. I will just show you, yeah, here you can find some computations. I just want to show you how these regions look like. So for such parameters, here we have the parameter space alpha beta defining. All right, I think that we have parameter space. We have parameter space delta, and we consider all beta transformations given by parameters beta and alpha. So this big triangle is our parameter space, and here I draw regions where the map has a corresponding primary NK cycle. So here we have primary 1, 2 cycle. Here we have okay. Here we have maps with primary 3, 1 and 3, 2 cycles, and so on. Okay, and yeah, and for us, the interesting part is that the symmetric beta transformations that corresponds to that serve as this reduction of Lorenz system, they correspond to parameter that lie on this red curve. So here we have parameters that define symmetric beta transformation, and we can observe that for maps with slope less or equal to square root of 2, we have primary 2-1 cycle. So we can study these maps using NK cycles and using renormalization theory because the maps with primary one cycle have renormalization f squared f squared. So yeah, we use this fact. So we use this fact that expanding Lorenz map with the primary cycles, they have renormalization f to the n, f to the n. And using properties of the maps with primary cycles, we proved that the set of periods of map F that have primary cycle is equal to n times q, where q is a period of some period of the q is in the set of periods of renormalization g, and here some n. So you can use renormalization g of the map F to describe the periods of such map F. Okay, so in our case of symmetric beta transformations, we prove that the map F beta with beta. Okay, I see I don't have time, so I'll just show you a picture. This result says that if you take any symmetric beta transformation from this, they defined by parameters from this orange interval, then their renormalization for any such parameter, the renormalization after rescaling is again symmetric beta transformation, but defined by parameters in this greater interval. And then again, you have map defined by parameter here. If you renormalize it and rescale it, then you will have a map from this interval. And you again renormalize it, then you will have map defined by parameters from this interval. And after, if you renormalize it, you will get a map from defined by parameters from this interval. So in fact, if you are interested in the study of periods of symmetric beta transformation, then you can just study periods of maps defined by these parameters, because then using this formula from the previous theorem, you can describe the set of periods of maps corresponding to such parameters. So we can focus on these parameters. And in order to study symmetric beta transformations defined by these parameters, we defined some polynomial, and the zeros of such polynomials give us a partition of this curve, and then we use this partition to describe how the complexity of periodic dynamics of corresponding maps changes when we increase parameter beta. So I will skip that, and I will just say the last thing. So what we obtain for the what information can we obtain for the attractor? So for example, we proved that for any parameter v in this set O, so the set of parameters corresponding to Lorenz system when we can deform it to one-dimensional map. So for any parameter v sufficiently close to some trifold parameter, the corresponding Lorenz system satisfies the following condition. So there exist infinitely many periodic orbits inside the attractor, and we can also say something about the first return map. We prove that the first return map has periodic orbits of all periods if we have parameter sufficiently close to some trifold parameter. So this is the one thing we can say about the attractor. We can also say that the dynamics of the first return map for parameters sufficiently close to trifold parameter can be semi-conjugated to beta transformation that is both strongly transitive and mixed. So okay, and another thing, we prove that if we take parameter v that belongs to this set O, but it's not a trifold parameter, then there are infinitely many periodic sequences that are not realized as itineraries of periodic points of the corresponding beta transformations. Okay, so we can say something using this symmetric beta transformation. We can say something about the attractor, but the problem is that for now this set of parameters T is poorly understood. We know that it is n non-empty. We know that it contains some open components, some open set, but we don't know a lot about this set of parameters. So we just can make statements like for sufficiently close parameters to this set. There are examples of such parameters, but yeah. So in particular, we cannot just take some. Okay, if we take some parameter for a Lorenz system, we cannot guarantee that okay, if you give me some parameter for the Lorenz system, they probably I won't be able to say that this for this parameter the flow can or cannot be deformed to one-dimensional map. So we should study more the sets of parameters. For now, we just know that such parameters exist, but we don't know a lot about it. Okay, so I think it's good moment to stop.
All right, we are a little bit over time, so maybe the one question. What's your call for you?
Eran Igra?
Krakow?
No. He's now in Shanghai Institute for Mathematics and Interdisciplinary. Sorry?
What is analytical work?
From Technical University.
So he was a PhD student from Princeton?
Yes.
I think he was here during the
I met him here during the time semester.
I wanted to ask like a general question about the parameters, let's say around the classical parameters. Is there a conjecture, let's say a conjecture that says we believe that in this region, for example, there will be infinitely many of parameters?
in the neighborhood of classical parameter.
Yes, but let's say, because I understand it's also about, being specific, as you said, not that there exists the neighborhood, but to give the neighborhood maybe.
And you ask
I mean, I'm just trying to understand what people believe.
okay, so for classical parameters, it follows from Tucker. Around this parameter, I don't know, but Kalitinski also proved that there are infinitely many periodic points, but for this triple parameter. So I'm not sure if it works around that parameter, but for some set of parameters. So
If measure of bad parameters. No, because then there is another question, which are points of density of the parameter.
Right. I don't know.
I don't know.
But I think there is some region where it all makes sense to ask these questions, right? If the parameters are too away, then probably it doesn't make sense.
Yeah, for example, in this set of parameters P, when you have all this cross section and the configuration is as
Okay, so let's thank the speaker again for the interesting talk.